Let's get started. Welcome to GDC 2026 Qualcomm sessions. Please silence your mobile phones. As per the policy, everything is being recorded here. Today, we'll be talking about every mobile renderer problem, like how to push more frame rates at low power, and how Infinity Nikki got there by utilizing the high performance memory. We have three parts of the session. First part, I'm going to cover the Vulkan API that exposes the high performance memory. Second part, Chris is going to talk about UE5 integration of the same Vulkan API. The third part, Yuhan from Infold Games will join us and give an overview of how Infinity Nikki take advantage of the Adreno High Performance memory. I think let's get started with the first part. This is a Vulkan-facing view of Adreno High Performance memory about the resource allocation and command buffer binding model and the best practices of using the Vulkan API. So what do we mean by the Adreno High Performance memory? It's an on-chip memory, which is low latency and high bandwidth memory. It is designed for improved power efficiency and high performance. Developers who uses this high performance memory can achieve significant power savings. And it's not just limited to one vertical, though we are covering only gaming in this session. You can imagine same patterns in compute-heavy use cases like machine learning, video, and image processing applications. Adreno High Performance memory is already improving the power and performance of many games. Some of the games I listed down here. It's not just for it's not just about using the Vulkan API, but there are some driver also uses the Adreno High Performance memory when the game is not using it. Okay, so how Vulkan exposes the high performance memory? We expose as a new Vulkan heap, which is the third heap, apart from the system heap and the protected memory. So from now on, rest of the presentation, high performance memory is also referred as a tile memory heap. Applications can query the size of the heap available. On different SoCs, there are different sizes available. We support both VK buffers and VK images in the tile memory. And there is a new usage flags added in the spec to denote the resources created can be bound to tile memory heap. So we support Vulkan buffers, uniforms, storage, texel, and also transfer operations. Vulkan images support storage, color, depth stencil, and also input attachment usage. So for images, the implementations vary, so you must query the driver with VK get image properties to find the formats and the size alignment requirements. So for example, here, so the size and alignment requirements vary for the tile memory heap, so applications should query using this API. The next step is use VK allocate memory, allocate. The key point is it always returns offset 0. It's application responsibility to sub-allocate, and memory aliasing is allowed on this tile memory heap. The last step is you bind the buffer and images, and that's all. So resource allocation is only half of the setup. The remaining half is this API also has a command buffer binding model. What is a command buffer binding model? So this new API is added for application to define the range of the tile memory heap that the application uses during the command buffer recording time. So all the accessed child memory resources must be bound to the same VK device memory object. So application can create multiple VK device memory objects for memory aliasing. Like shown in this diagram, two different colors, so application can bind two different memory layouts for memory aliasing. So one key point is the Vulkan driver will use any unbound memory for internal optimizations. So application shall try to bind only required memory so that it doesn't kill driver optimizations. So one important life cycle note. Tile memory is unbound at the end of the command buffer implicitly. So if the application needs to persist the tile memory across multiple command buffers, it must have to bind at the beginning of every command buffer. So let's concrete that with an example. And in this simple example, we have one VKQ submit with two command buffers. If you see the first command buffer, the first compute batch doesn't bind any tile memory heap. It doesn't define any range of the usage, so driver can go and use it. So another important thing that I want to highlight is if application, in this example, the application is binding the tile memory in the beginning of the second command buffer, so the tile memory is persistent across these two command buffers. Like I said before, if you look at the top right corner, whenever it says red, it is undefined from the application point of view. All those undefined regions, the driver will use it. So make sure that you bind it properly and use the Vulkan validation layer, making sure that the binding points and the regions defined are accurate. Okay, so moving on, we covered all the API mechanics. So how you can choose what resources go into tile memory heap? The best candidates to put in the tile memory heap are the resources that are used multiple times within a frame and can be discarded at the end of the frame. The classic example is the G-buffer surfaces, like shown here, like albedo, normals, and depth. Those are used multiple times within the frame and can be discarded at the end of the frame. So, and make sure that you use Snapdragon Profiler to measure the memory bandwidth of each surface, because tile memory heap or the HPM is limited on chip memory. So use Snapdragon Profiler and identify the high bandwidth resources, and so that you can place them in the tile memory heap. Moving on, this extension is available on Snapdragon 8 Gen 5 for Android and Snapdragon X2 Elite and Plus platforms for Windows and Linux. We have also added the validation layer support. There is a version of the validation layer. And I provided more resources of Vulkan spec, and also there is a sample repository, GitHub, that I pointed out there. So overall, use tile memory for high reuse and short-lived resources. And it's a very simple API and a very few lines of code to integrate into the game engine backends. Next, Chris is going to cover the UE5 integration of tile memory heap.
Thank you, Srihari. I'm Chris from Snapdragon Game Studios, and I'm going to walk you a little bit through our Unreal Engine 5 integration. So the Because the tile memory heap works a little differently from the rest of the heaps, specifically it is very small, it's only meant for transient allocations, and all the allocations overlap and start at index 0, or offset 0 rather. So it seemed more trouble than it was worth to reuse the existing tile heap objects in UE5. So we created our own, so it takes care of all the memory alignment and everything. And so you can allocate either buffers or images out of that new heap. And because the render dependency graph in UE5 has full knowledge of the frame and the resources, like when they can become invalidated and so on, it seemed the best place to add some new flags that let you tag which resources should live in tile memory. And then the Vulkan command buffer class will take care if any resource used in the command buffer uses tile memory, it will automatically bind the tile memory objects at the beginning of the frame. And the implementation will let you put multiple resources in tile memory and figure out all the correct offsets and alignments. And it supports, it's render agnostic, so it supports both the Vulkan ES31 mobile renderer and the SM5. And you also have new pixel format capabilities that will let you query the driver to see if tile memory usage is supported for a given format, as well as check whether transfers are supported, which will then let the engine use the fixed function clears and like fill buffer and copies. Otherwise, it will fall back to shader-based UAV equivalents. The feature can also be disabled using a new console variable, so that can be useful when you want to get render dot captures or something like that. And there's some new commands that we added, such as dump tile heap memory, that will let you inspect the free ranges and the resources bound. So to showcase what tile memory can do, so we developed this Project 1 cinematic. It's running in Unreal Engine 5.4.4, entirely created internally, and it features all the bells and whistles of the SM5 renderer, so nanite, lumen, virtual shadow maps, and so on, all working concurrently. And it's running at 30 FPS on our latest flagship device. I encourage you to check out the blog post that we released last year. It provides a lot of practical information on how exactly we reach our performance targets, going over scalability settings, console variables, changes to the content, how to make nanite and lumen work best on mobile. There's a lot of good stuff in there. So here's the video. So we experimented with a lot of different resources to try and find the best bang for our buck, and it ended up being the Nanite 64-bit visibility buffer. So it's the perfect candidate. There's a lot of access throughout the frame, and we got some pretty good memory bandwidth improvements by putting it in high performance memory. But we had also tried like the scene color and various other buffers and images. So we provide reference implementation for UE 5.5 and above. It's posted on our public GitHub fork of the Unreal Engine. So it features a string console variable that lets you quickly play with various resources that you might want to be able, that you might want to put in high performance memory. So it supports wildcards as well, and you can quickly experiment and use Snapdragon Profiler to verify and validate the impact on memory bandwidth. And once you find a good candidate, then you can go ahead and specify the tile memory flag when the RDG resource is created. And in addition to the branches themselves, we also have standalone like GitHub releases, so patches that you can just drag and drop into your engine that should apply cleanly on top of the relevant official release by Epic Games. And in order to access the repo, you will need to follow the same access requirements as the main Epic Games Unreal Engine repo on GitHub. And with that, I'm gonna pass it to Yuhan, who will show you how Infold Games took advantage of high-performance memory in Infinity Nikki.
Thanks, Chris. Good morning, everyone. I'm Yuhan Zhou, a game engine developer from Infold Game, and it's my great pleasure to be here, GDC 2026, to share with you the mobile optimization work of Infinity Nikki on Qualcomm platform. High-performance memory can significantly improve the power efficiency, and my talk today will focus on power optimization, and I will also share some power optimization tags used in our game. There are three parts: the mobile rendering pipeline, landscape optimization, and asset optimization. Everything we will talk about has one clear goal in mind: to keep the game looking great and running smooth on mobile. That's really important for a visually heavy game like Infinity Nikki. First, we will talk about the mobile rendering pipeline on Snapdragon. And the first big optimization is the tile memory heap. This is built for Adreno GPU on SM8850, the Snapdragon Elite Gen 5. There is a 14.2 megabytes tile memory heap available. And the main idea here is simple. We can manage tile memory directly in our game instead of letting the system handle it automatically. By managing it directly, we cut out a lot of bandwidth overhead and make the most of the on-chip memory. Here's what mentioned by previous two speakers. And one really important rule: the tile memory boundary is the Q-submit boundary. In Unreal default mobile pipeline, there were two Q-submits, one right after default shading pass, and the other at the end of slate rendering. To better utilize PG memory to fit both color and depth into PG memory, I removed the first Q-submit. And this slide shows the RTs I stored in PG memory. For example, scene color, scene depth, SSAO RT, and bloom intermediate textures, GSR intermediate textures. Up to 12 RTs were installed in the tile memory heap within a single frame. The total size is slightly larger than 14.2 megabytes, is 14.7. And I will explain later how we exceeded the memory limit. This slide shows how many times depth and color are used in our game after default shading pass. For scene color, we have 4 times read and write per frame. For scene depth, we have 6+ times read and 2 writes per frame. Before high performance memory, there was almost a fixed cost. But now, if you store color and depth into the tile memory heap, that means all the later reads and writes to color and depth are totally free. No more bandwidth at all. There is a huge optimization for us. The overall read and write bandwidth overhead has been reduced by more than 20%. Next, I'd like to share some tips we have used in our work. For this slide, I will explain how we exceeded the memory limit. By default, the final RT GSR.max color cannot fit into tile memory heap because the space is not enough. And the default alignment will cause memory overlap, and that leads to visual artifact. We manually controlled the memory alignment to completely avoid overlap. During the GSR pass, the intermediate RTs for AO and Bloom are no longer needed, so overwriting them won't hurt the image at all. By this way, controlling memory alignment, we can fit more images. Here are some very important notes. First, let's talk about the depth stencil RT format. We recommend using D24S8 instead of D32S8. The first reason, D30S8 uses 9 megabytes of page memory if the RT is 720p, but D22S8 only uses half, 4.5 megabytes. And the second reason, D32 may cause some display artifacts. Second note, there is a temporary restriction on copying images in page memory. Bleed copy operations are not supported for page memory images in some driver version, whether they are the source or the destination. Instead, you have to use pixel shader for copying. Qualcomm has fixed this issue in their latest driver. But if you still get the screen flickering, just try use PS draw for copying. The last note, different chips may have different tile memory heap size, so that's really important to have adaptive scheduling that works with these different sizes. The second topic is in mobile rendering pipeline is AFME. We built AFME right into our pipeline. First, we use GPU calling / draw course from the start, use compute shader. And when past default shading, this cuts bandwidth overhead a lot. When post-processing ends, we send the motion vector, depth, and color data straight to AFME. AFME takes the frames data, combine it with the last frames, and generates a new frame. That's how we keep performance smooth and cut power use drastically. We tested 3 modes. As you can see, there is a 36% power drop, while still keeping a stable 60 FPS. Next, let's talk about our custom SGSR2 optimization, path merging. We used to run upscale and tone map as 2 separate passes. Each would read and write to system memory independently. And remember, the tone map path uses the back buffer resolution because it runs after GSR upscale path. So this directly increases the ALU compute and bandwidth cost of the tone map path. Now we merge them into 2 sub-passes that share data through tile memory, use frame buffer fetch to replace texture sampling. the tone map just read directly from what upscale wrote. And the result, we cut read bandwidth by 35% from 60 megabytes to 10.3. Secondly, we will talk about the mobile landscape rendering optimization. Infinity Nikki has a huge open world, so landscape optimization was a must. Our landscape rendering is built on 3 core technologies: runtime virtual texture for high-quality near-field terrain, streaming virtual texture for performance 5-field rendering, CDLD to render the entire terrain in just 1 or 2 draw calls. Here's the first optimization for RVT, ASTC compression. We use the ETC compression at the first. It's still the mobile standard, but it makes terrain look blocky and washed out. We swapped it to ASTC 4x4, use computer shader, and you can see the difference on next slides. ASTC show way sharper details and better colors. This image shows the result of ETC compression. If we look to the bottom left, you can see obvious blocky artifacts on the terrain grass. And this image shows the uncompressed version. The blocky artifacts are completely gone. ASTC has no blockiness either. You can barely tell the difference between ASTC 4x4 and the uncompressed image. And it's not just a visual win. ASTC also cuts bandwidth overhead. Compared to uncompressed RVT, the memory usage is only 25%. Using ASTC for RVT compression brings huge gains for both quality and performance. Our second optimization for RVT, color RVT mid-range optimization. If you need to reduce the performance overhead of RVT, you can do so by reducing some levels of RVT. And this approach will cut the highest detail MIPS to save on performance. It also means using a lower precision RVT. So player immediately noticed the blur near field terrain. So we flip it. We cut the lowest detail RVT layer instead and filled the gap with the highest detail SVT color data. This layer only affects the far field, which SVT already handles. As you can see, the colored areas use RVT. Different colors represent different MIP levels, and the distant part use SVT. We can count distance RVT without impacting nearby RVT MIP level, just like that. And for this demo, I removed more layers than usual to make the difference of views. In the result, 100% near field detail perceived, and we still get the performance boost, no trace-off at all. And the second advantage of this optimization, we can support much larger maps with the same RVT performance cost and SVT quality levels. This is the third optimization related to RVT. This is once all but slashing GPU memory overhead with frame buffer fetch feature. Sorry. Yeah. Originally, we need 3 render targets during the color RVT draw passes. Even though the final color output only uses 2 physical textures with 8 channels, this is directly because of the alpha blending. We need it for terrain color blending. It's kind of a waste of bandwidth because there can be thousands of VT tile copies in the game. We use the frame buffer fetch to restructure the RT channels, cut to 2 RTs for high material quality and no visual loss at all. Using 1 RT for low material quality, and even with 1 RT, we still support opaque and mask rendering, no feature lost. Using 2 RT saves 30% of GPU memory write overhead during the VT draw pass. Using one RT saves 76 of GPU memory write overhead, and also reducing the VT compression compute cost by 50%. Here's our fourth optimization about RVT. This is one of the methods we use to solve mobile terrain problem, real-time layer blending. PC lets our artist blend 10 of textures layers to reach terrain, but mobile GPU cannot handle that. Way too much bandwidth, and we didn't want artists to rework all their work for the mobile version. So we built an automated solution. In editor, you just need to set up the layer info replacement rules, like the red box. And then switch to mobile preview. You can see the replaced mobile landscape. During the packaging process, the system auto-replaces the marked layer info and merge maps, generates optimized mobile material all by itself. For example, if you previously had 9 layers in the landscape component, you would need 3 weight maps to store the weight value across 9 channels. By replacing just 1 layer, then get merged into 2 weight maps from 3, as only 8 channels are now, and the sample count was reduced by 1/3. Artists keep making PC quality terrain, and mobile automatically gets a replaced version with no extra work from artists. The number indicates how many weight blending layers are used on this landscape component. The first one is PC version, and then the mobile version. PC version color and the mobile version. Now, on to streaming virtual texture, our zero-cost distant grass trick, which is all about swapping runtime work for build-time work. Rendering far-field grass is a disaster on mobile. Tons of draw calls, after testing, useless vertex processing, and player only see tiny specks anyway. So we bake distance grass and foliage colors directly into the color streaming virtual texture at build time. No more 3D geometry for far grass, and it's just part of the terrain texture, part of streaming virtual texture. Zero runtime performance cost. As you can see on the screen, this one is before this optimization. And please look at the center of the screen. After this optimization, we can see the sea of flowers with no performance cost. Next up is the final section, asset optimization. To make the world rich and varied, artists create many unique meshes, but most of these meshes are used very infrequently. Meanwhile, many of these meshes are quite similar in shape. This is fine on PC, but it causes performance issue on mobile. This leads to not only more draw calls, but also more memory usage, more bandwidth overhead. Mesh replacement is our mobile solution to this big problem. We built a simple and powerful system inside Unreal Engine. Artists only need to set a replace mesh on any setting mesh asset, like the red box. The system will automatically apply the replacement to the scene for all components that use this mesh, including static mesh component, ISM, HISM, foliage component, and landscape grass, with real-time edit preview and automatically transform adjustment. This video will show the real-time preview of replacing meshes in the editor. Use the console command, you can replace the 4 bags of different size, different styles with just 2 styles, while keeping their transform unchanged. these 4 bags for stealth. Yeah, just like that. Here we show the scene before mesh replacement and this after replacement. This one is before replacement. After. To clearly see what has changed, we also create a debug view. Before replacement, after when? At mobile packaging time, we merge identical replace meshes into one instanced batch. And we kept the number of meshes in the same and optimized by reducing the number of mesh types. As a result, GPU time is down 20%, draw call are down 10%, and the world still look diverse. In brief, we have covered a range of mobile power optimization tasks today, and high performance memory has been a real game changer, reducing our overall memory bandwidth by more than 20%. This result truly exceeded our expectations, and we are very excited to share them with you.